Right, okay, so last time we were talking about vector surface integrals. Remember, vector surface integrals represent flux. Why are we interested in flux? Well, the only example we've seen so far is that it can help us understand how much fluid, in whatever appropriate sense, how much fluid per unit time is passing through a surface. Okay. All right, now I want to show you a couple more computational related notes. So specifically, let's see, I'll go ahead and expand this. That helps. Okay, so yeah, sometimes you get lucky. Don't let the lucky opportunities pass you by. You want to cash in whenever you have a cool opportunity. So now here is an example question. And notice it doesn't say anywhere in the statement of this question, awesome geometric opportunity here, right? So you have to be on the lookout for this kind of thing. All it says is we're going to compute a flux. So we want to look carefully at the geometry and see if we can maybe get any opportunities for lucky breaks before we resign ourselves to parametrizing and going through the sometimes laborious process of cranking out the computation. Okay, so in this case, our domain is a sphere. Sphere centered at the origin. And spheres centered at the origin have some really nice features about them. They're symmetric, that's cool. They are lots of other neat things about them. The distance from any point to the center, constant. That can be useful sometimes. In this case, we're going to use the fact that the normal vector is easy to write down. The normal vector, in this case, is going to be a scalar multiple of the position vector, because I argue as follows. Spheres, centered at the origin, being what they are, the position vector is a radius. And spheres have the feature that a radius is always perpendicular to the surface. Well, the normal vector that we're looking for is, of course, also perpendicular to the surface, and therefore these are multiples of each other. And specifically, since the blue vector has a magnitude of 3, the unit normal vector is going to be 1/3 of that. What do you think? Does everybody buy that so far? Okay. Now, who cares? What is this? How does this actually help us? Maybe not, to be totally honest. I mean, the flux, I can rewrite flux like this, and then I can plug in my little conclusion here that the unit normal, orientation unit normal vector is xyz over 3. Plug that in. Does that help me? Well, again, maybe not. My vector field, though, I can plug that in. And here's where we start to notice the good news. You can crank out this dot product. That dot product is obviously 0, and we're done. So we got lucky. Right? Now, I'm not saying it'll always be this nice. I'm not even saying that when you have a sphere, it'll always be this nice. What I'm saying is if you have a domain that is a sphere centered at the origin, this is worth a look, right? It's worth checking out just on the possibility that you might score like we did in the case of this example here. Does that make sense to everybody? So just keep an open mind and be on the lookout when there's a possibility of awesomeness. Yes?
Yes, I'm sorry, but could you please repeat why it's 0?
Yeah, you just multiply it out. Yeah, this times that plus this times that plus that time, it just adds up to 0.
Oh, okay.
Yep. Just the algebra.
Oh,
Yep.
just
Yeah. All right, now here is another different kind of geometric convenience. A bunch of details you'll notice in the statement of the question. Let's not get lost in those details. Note, again, we're computing a flux. So again, I'm going to observe that I can rewrite flux in this way, where I not assuming that I'm going to start with a parameterization, but I want that orientation unit normal to be visible so that when I identify what that is, I can just plug in for it. In this case, what I'm going to notice is that our surface whatever that is, our surface is part of this plane, y equals 3. It's a very specific part of that plane, sure, of course, right, absolutely. But that plane y equals 3, if you're talking about part of the plane y equals 3, I can tell you exactly what the normal vector is. That normal vector is going to be 0, 1, 0. Or, I guess, depending on the orientation, it might be 0, negative 1, 0. But just by virtue of being part of that plane, we pretty much know what the normal vector is. Now, conveniently, it says oriented in the positive y direction, and so that's why I know it's this exactly. So I can plug that in, my normal vector, 0, 1, 0. Okay, now, is that enough to make the problem go away? Not quite. We do have an ugly vector field. We're going to have to deal with that. But here's the thing. The fact that y equals 3, the fact that we're in this plane, has more than just a geometric convenience. It also has an algebraic convenience. That goes there and there. Right? Every point in my surface is on the plane y equals 3, so y is literally 3 everywhere that I'm interested. So plug it on in. And notice this thing, that second coordinate, just turns into 0. And so that coordinate turns into 0 as well. In some sense, I haven't really done any real work yet. Right? I'm just kind of noticing freebies that come along for the ride immediately, simply from the fact that my surface is inside of this plane y equals 3. Everybody good? And so again, will this always solve the problem for us? Not really, but sometimes it does. It's I think always worth a look. And in this case, this dot product again always equal to 0, and so therefore the integral is equal to 0. And so again, we score. That possibility is why it's always worth checking it out. What do you think? Everybody happy? All right. Okay. So y'all will recall, I imagine, that when we were doing vector line integrals, there was this weird notation called coordinate line integrals that we were able to write down, and it's just kind of a clunky, awkward notation that has its moments. Again, in a more sophisticated context, it's very powerful, very important, etc. But in practice, for us, it's just kind of a clunky notation, and I just had to show you so that you'd be aware, because you're going to see that clunky, awkward notation in various different contexts, and you got to know what to do with it when you see it. So, same story here. It's a little bit different in terms of how it plays out. It's going to play out off this formula where I'm going to expand capital N as that, which I will further expand those partials by coordinates, which I will further rewrite by actually cranking out that cross product. And you may recall from, end of 7.1, I think, that those coordinates end up being mysteriously two-dimensional change of variables stretching factors. Very weird, very counterintuitive. Very non-intuitive. So that having been noted, let me point out that we can take then this new formula for our ds vector, distribute the differentials, those scalar differentials on the outside. And now let's just ask the reasonable question, how would we interpret these coordinates, right? How would I interpret, for example, this right here, dx, dy, ds, dt, ds, dt. And again, flashbacks to when we were doing change of variables. The whole reason we write this stretching factor here as a fraction is because it in some loose sense, and again, major math crime here, and don't hold it against me, it acts like a fraction in a lot of ways, right? And this is one of them. And so the reasonable Oh gosh, and again, cringe. Oh gosh, don't tell my old math professor I did that. If you pretend and infer as you usually would, it would make sense to write this as dx dy. And there is a really good geometric justification for this, and I'm happy to show anybody that comes to office hours with curiosity on this point. This actually makes really good sense. In fact, the third coordinate of the ds vector very naturally does relate to literally a piece of area in the xy plane, as this notation kind of suggests. So this is not just notationally reasonable, this is geometrically meaningful in a really nice way. So anyway. Okay. All right. So with that established, and again, the whole point to this is that we were rewriting our ds vector. We have what you might call a coordinate notation for our ds vector. So let's stick that in here. And keeping in mind that our vector field has coordinates, let's call them PQR. Then crank out the dot product. And that dot product multiplies out to be that. I didn't really do anything, right? Again, I'm just kind of rewriting things. And what we have then is that you can rewrite, let's see here, you can rewrite flux integrals as what I'm going to call coordinate surface integrals. Which again, I encourage you to think of these as just an alternative notation for vector surface integrals. Okay, why and who cares? Well, we care because this notation, oh gosh, this little speech is a lot like the one I already gave for coordinate line integrals. It comes out of differential forms. It's very powerful. It's ultimately very natural. This is how you prove various significant, important theorems. This is no joke, a big deal, very useful. Just not going to be stuff that we see in this class. But because it has all these powerful features, this notation, clunky though it is in common use. You are going to see this notation outside of Math219, where I have no control over notations that people will use, right? So you're going to see this, and so you need to make sure that you know what to do with this when you see it. Now, what I encourage you to do, this is just my take, I encourage you, every time you see this, to just realize they're talking about a flux. It's just a different notation for a flux. dy dz, dz dx, dx dy is just a clunky way of representing the ds vector. And then correspondingly then, these coefficients are just telling you what the vector field is that you're taking a flux of. Right? And just make sure that you get these differentials in the right order. Which product of differentials is which coordinate has to be exactly like this. So do be careful, heads up. When you see this kind of thing, just reinterpret, this is what I do anyway, reinterpret as one of these. It's a vector surface integral. Okay, what do you think? Questions? Everybody happy? Yes?
So can you just use this at any time to discuss flux?
Yeah. Anytime you want to write down flux, you are perfectly within your rights to write it this way instead. Again, in practice, it's not very many circumstances where this is actually going to be more convenient. Never say never. There are those times, right? But I'm thinking more in terms of when you encounter this, not of your own free will, right? What do you then do with it? Yeah. All right. Okay, moving along. Symmetry. We can be quick with this one. You can probably even guess what's about to happen. You may recall when we talked about line integrals. For scalar line integrals, symmetry as usual, have fun. For vector line integrals, there is no symmetry theorem. It doesn't work. Landmine, watch out. Don't try to do it. It doesn't work. Okay, Exactly the same thing is true for surface integrals. For scalar surface integrals, you have an odd symmetry theorem. Just like every other odd symmetry theorem we've seen, both conditions have to hold. It's got to be the same symmetry plane for both of them. Scalar surface integrals, exactly what you would hope and expect. Again, use as much as you like, have fun. And as you would expect for vector surface integrals, there is no odd symmetry theorem. It doesn't work. And it doesn't work for pretty understandable reasons. If you look at your vector surface integral, and if you choose to write it like this, and if you then say, okay, what about that normal vector? How does that normal vector look on the picture, and does it behave in a way that's nice with respect to symmetries? And is this going to do what we want it to do? Well, no, it just doesn't. Right? That normal vector, it's just not the same on both sides. The DS areas are, right, that little piece of area and this little piece of area, those can be the same. Yeah, sure, no problem. If you split it up the right way, yeah, that makes sense. But the normal vectors, they're just different. Game over, we lose. So, landmine. Please don't try to use an odd symmetry theorem for vector surface integrals. Does that make sense? Great. Okay. I commented on some of this as we were developing vector surface integrals, that certain things that we were doing kind of were somewhat analogous in a way to certain things we had done with vector line integrals. I kind of want to bring that all together and just sort of summarize as much as I can in this context. But before I do that, I want to give you a quick idea of why that is. It is not a coincidence. This is just a cultural point. Again, I think it's useful for you all to know, in some sense, what's a coincidence and what's not a coincidence. Right? Why line integrals and surface integrals have so much in common is because they are both examples of integrals of differential forms. They are literally the same thing in different contexts. Exact same idea, integral of differential forms, just, different geometry and different kinds of differential forms. Anyway, once you have that once you realize that they are just the exact same thing in a different context, well, of course they have things in common. They're the same thing, right? You would expect that they should have a tremendous amount in common. So that's, again, just a good thing to be aware of, that this is not a coincidence. So summarizing, let me zoom a little bit here. Here we go. Everything that I have on the screen here is old news. There's nothing new on the screen. All these formulas we've written down previously. When you want to talk about line integrals, you parameterize the curve. There are various players that we discussed, the velocity, the unit tangent vector, the dx vector, etc. And they all relate in these various different ways. All of these formulas are, like I say, old news. Most of these, in fact, we wrote down back in Chapter 3. And then we, started using them again quite a bit in Chapter 6. How do we do surface integrals? Well, again, we parameterize, and then we had various players. Capital N, and the ds vector, and the ds scalar, and this, that, and the other. Right? And again, lots of different players. Long story, and I'm not going to reproduce, of course, all of that. So here's the strength of the analogy. I like to use colors here to show how strong the analogy is. So parameterization on both sides. And in both sides, in both of these stories, geometrically different, of course. Different physical applications, of course. In both cases, there is what I'm going to call a derivative. V is literally the derivative of the parameterization. N is, it's a cross product, but a cross product of derivatives of the parameterization. So pretty analogous. And look where they show up in these equations. They show up in pretty analogous places in those equations, laid out as I have, kind of appropriately. Okay, unit vectors in those directions are our orientation unit vectors, and so I've got t and a little n, again, totally analogous. I've got for each one of these a corresponding little piece of our domain. I can talk about the length, the size of that little piece of curve, ds. I can talk about the area for size of this little piece of surface. And again, look where they show up in the equations, totally analogous. Okay? And then we proceed. Let's look at the vector differentials. The dx vector shows up there and there. The ds vector shows up there and there. What you might call the parameter differential. Let's see here. Did I run out of colors? Okay, I'll use red. Okay, the parameter differentials representing parameter size there, dt. Over here, the size in the parameter space, ds dt, shows up there and there. Also analogous. All the players relate to each other in perfectly analogous ways. Isn't that weird? I think it's an eyebrow raiser. I think that's highly fishy and suspicious, strongly suggestive of, I think there's something relating these two stories, right? And again, there is. Both of these are, in fact, special cases of the same construction that we're not going to talk about. And you don't need to understand what that construction is to appreciate and capitalize for your own purposes on the fact that these analogies are this strong. So again, for example, to whatever extent you feel like you do understand something happening in the story on the left, that's a guide, kind of a hint of how to think about what to expect from the analogous player in the story on the right. So, an opportunity to help make some sense out of things. Yeah?
In what scenario would we use this sort of analogy?
Oh, just as you're trying to understand things. So, for example, if you feel like, I never really quite feel like I understood what the deal of the ds vector was. Well, you note in this analogy that the ds vector is analogous to the dx vector, so you can translate your question to, what's the deal with the dx vector, right? And to whatever extent you understand what the dx vector does in this story, you can expect, hope, that something analogous in some sense is what you should expect out of the ds vector in this story. Yeah. So it's just an opportunity to guide yourself by, expecting a lot from the analogy. Yeah. Okay. So I think that's worth mentioning. Let's see here. I will zoom out just a little bit and point out, yes, we also have various additional formulas about vector line integrals, vector surface integrals, and again, we've talked about most of these forms of these integrals previously, and if you were to take my little color pattern and extend down here, the pattern continues. I just don't want to use the precious class time for fun with colors, right? But the analogy does continue, and it's worth thinking through, in all of these equations. Okay. All right. So that does it for 7.2. We're going to move on to 7.3. This is an enormous section, probably the biggest one in the book. You remember I've joked in the past about this author likes the occasional monster section that really ought to be 2, maybe 3 sections. And this, I think, is probably the biggest one in the book. It's going to take us the rest of the semester, pretty much, minus probably 1 class day to finish. I'm sorry?
Just one section.
7.3 is a monster. It's going to be most of what we're going to do. Of course, we don't have that many class meetings left, right? Let's see, what do we have?
4, 3.
Yeah, not including the exam.
3.
Golly, really? Is it 3? Oh, geez. Okay, all right. Well, yeah. So it's gonna be a tight semester. It's always tight. It always works out. And by the way, I do have a bunch of stuff in the notes that is pretty optional. that it's starting to look like we're not going to be able to do, and so be it. It's going to happen, but it's going to be fine. No problem. Okay, so a lot to say in section 7.3. The book starts with Stokes' theorem. I prefer to start with Gauss's theorem. I think it goes down a little easier. I think it's a better little sort of first step in the three-dimensional accumulation theorem arguments. And I'm going to start with Gauss's theorem. In order to do so, we need to talk about boundaries. Now, some of this you already can imagine if you have a solid three-dimensional region. So something kind of like this. Imagine that you have Play-Doh, right? And you kind of trap some air inside of a lump of Play-Doh. It's actually a three-dimensional solid thing, and there is thickness in the Play-Doh. The Play-Doh is a solid, but there's a kind of a air bubble in between, right? Something like this, just as a for example. And I think you could probably imagine that the boundary is just the border between where the Play-Doh is and where the Play-Doh isn't. Right? So there's kind of a round sphere sort of thing that is the what you might call the outside part of the boundary. But then, of course, don't forget there is also the inside part of the boundary. For this particular solid, it's a little bit of a weird solid. It's got this air bubble in it. And so when you say, where's the border between Play-Doh and air? Now there's some border of Play-Doh and air here as well. Right? So, reminder for the rest of chapter 6. Oh, yeah, go ahead.
Oh, sorry, just after your...
Oh, okay. For the rest of chapters 6 and 7, the word boundary means oriented. Right? This is a loaded word. That's just what it's always implied at this point. Boundary means oriented, always oriented according to certain conventions. The convention here, when you're talking about a boundary surface of a solid in 3 dimensions, the convention is away from the solid, away from the Play-Doh, right? Such as what I have drawn here. Yeah, you had a... Yeah,
so my question was just, like, after in the last exam,
yeah.
we had examples similar to this, and we would write, like, a triple integral. How is this, like, a different approach?
I'm not sure what that means. I'm sorry.
Where we would have, like, R is from, like, the R bound, and then, like, functions in 3 space to solve for volumes like this.
Oh, you mean just like a triple integral?
Yeah.
Oh, yeah. Oh, no, I haven't actually said anything yet as part of the story yet. So we're eventually going to be making a statement that will involve a triple integral. Right now, I'm just defining stuff. I haven't actually gotten to the point yet where I'm making a statement yet.
Oh, okay.
Yeah. So for the moment, I'm just telling you what the word boundary means. Yeah. And it's going to take us a while to build up to an actual conclusion here.
Okay,
Yeah. Yeah. No worries. Okay, so away from the solid. So just a reminder, this is on y'all, right? It's part of your job as students. When you see the word boundary, you got to remember, boundary. That's a loaded word. Boundary means oriented. Oriented is according to certain conventions. Our convention here for a boundary surface of a solid 3-dimensional region is oriented away from the solid, like so. And keep in mind, sometimes that's outward. A lot of people misunderstand this as being always outward. It is not always outward. Sometimes away from the solid is, I think you'd have to call that inward. Right? But that's what away from the solid is at this point, not always outward. So, again, common misunderstanding, and that leads to wrong answers. Yes?
If we're given a solid like this in the problem, will they specify inward versus outward?
If they say the word boundary, then that is the specification. The word boundary means this. Boundary means oriented according to the standard convention, and this is the standard convention. Does that make sense?
Yes, but like there are 2 like ends for this specific example.
There are 2 what? 2 what now?
2 like end vectors.
this is what I would call one orientation on this one. So I mean, you could say that this surface has two chunks, sure, right? There's the outside chunk and the inside chunk, but we don't really have to break it up that way. This is a boundary surface. It's a surface in two pieces, and it has the standard orientation that follows the rule, which looks like this on this chunk, and it looks like that on that chunk. But in both cases, away from the solid. And all of this is implied going forward by this word boundary. Is that, you don't look happy?
Sorry.
Okay. We can talk more after class if you want. Yeah. Okay. Yeah, yes.
So just to confirm, like based on this picture, they're not the same function?
Function? What function?
Like the circles they're not meant to be like concentric circles.
No. Yeah. No, this is just a lump of Play-Doh. Yeah. I tried to, believe it or not, this is not artistic incompetence. I did try to to make it look asymmetric. It's supposed to be thicker over here and thinner over there. Yeah.
That's right.
Yeah, no, this is an arbitrary lump. I wanted there to be an air bubble so that I could point out that it's not always outward, but this is just an arbitrary solid. Yeah. Okay, so that's what boundary means. Again, always oriented, always according to this convention. By the way, as usual, totally arbitrary, right? If the mathematical community had made a different decision long ago, this could have been toward the solid. But that's not the decision that got made. It doesn't matter, right? Ultimately, what that decision was at the time. But now that it's been made the standard, it is the standard, and we got to stick with it, arbitrary though it is. Okay. All right. Now, reminder. Back in chapter 6, I made a general argument about this thing called an accumulating quantity, right? And I made the observation that, look, all you need is to know that you have a quantity that has this feature. If it's an accumulating quantity, whole is the sum of the parts, then I can view it as a kind of a stuff. I can view it as distributed across the solid, across the interior of whatever your domain is. And if it's a stuff, then you can talk about a corresponding density, stuff per unit volume. And if you have a density, well, total amount of stuff is just an integral of density. Right? So this applies to any sort of accumulating quantity. And mass is my favorite example. It's the easiest first example. Mass is an accumulating quantity. You can view it as a kind of stuff. It actually is a kind of stuff, so that's convenient. But even if it wasn't, you could view it as a kind of stuff. It has a density, and you compute it with integrals. Okay. So with this convention in mind, I'm going to now tell you a new accumulating quantity. And the new accumulating quantity is boundary flux. Boundary flux accumulates. Now let's make sure that this is right. Let's be careful about this. Specifically, you'll notice I say here accumulates over volumes. What that means is that if you have a whole volume and then you split that up into pieces of volume, sort of a left piece and a right piece, that this quantity, boundary flux, for the whole will be the sum of the parts. Right? Specifically, though, where we split up the volumes. Okay, so let's check and make sure that that's true. By the way, you probably recognize this picture, or at least this looks a lot like a picture that we drew long ago. We drew a sort of a two-dimensional version of this picture. And this is just the three-dimensional version of the same thing. The intuition for why this is going to work is morally equivalent to why that last one worked. And let's just look one piece at a time. On the left piece, boundary flux, oriented outward, of course, is oriented like that. On the right piece, boundary flux, oriented outward, of course. Looks like that. Do these add up as they're supposed to? Well, wait a second. I'm concerned about this shared face. On this shared face, this shared face isn't part of the boundary of the whole. The whole, the great big lump, the boundary is just kind of around the outside. What's going on with this face here? That isn't supposed to be there. But here's the thing. It shows up twice with opposite orientations, and so they cancel. Just like we saw for the two-dimensional divergence theorem, just like we saw for Green's theorem. I mean, different geometry, but morally kind of the same thing, right? This kind of thing is inside of all of these, what I like to call accumulation theorems, for exactly this reason. Okay, so those cancel. What's left truly is the boundary flux for the whole, and we win. The whole is the sum of the parts. We have a new accumulating quantity. And beautiful thing about this, we've already made all of the general arguments about what to do once you have an accumulating quantity. If you have an accumulating quantity, we're going to interpret it as stuff, whether we see it that way or not, right? We're going to interpret it as being as kind of a visceral, kind of a stuff distributed over the interior with a resulting corresponding density, stuff per unit size, and we're going to compute it with an integral. That's what you do with accumulating quantities. So, here we go. I'm going to view it as being stuff distributed over the interior. Now, of course, flux actually is computed on the boundary. After all, it is literally boundary flux, but it behaves as if it's distributed across the interior, because the whole is the sum of the parts. So this is how we want to think about flux. Try not to think about flux in this sense. Try to think about flux as being a stuff distributed through the interior. And in that sense, if it is stuff distributed through the interior, you can talk about the resulting density. Right? Flux density means stuff per unit size. The stuff in question, of course, is boundary flux. Right? Flux, outward oriented, of course, that's our convention. Outward oriented boundary flux. Density means stuff per unit size, in this case, volume. So flux per unit volume means on each little piece of volume. I drew a two-dimensional instead of three. It's easier to draw. That's all. Imagine a little three-dimensional volume here. But if you have a little three-dimensional volume, you can talk about the outward-oriented boundary flux. You can divide by the volume. That's what we call flux density. And that goes by several different names and notations. Divergence, or flux density. Div, of course, is an obvious abbreviation of divergence. Del dot, of course, we talked about back in chapter 3. Convenient, very common notation. You're going to see that a lot. And here's the formula for it. Not so bad, really, to justify that formula, but it's, I think, just kind of a computation, and I don't think it's best investment of time. I think what I want to make sure that you understand, what I'm most interested in, is that you know why we care about this formula and what, how to visualize this and what we're going to do with it. This formula is flux density. This is telling you how much of this stuff, this flux stuff, there is per unit volume, and therefore, what we're going to do an integral of to compute flux. Okay. So I'll come back to the comments down here in a moment. Let's just put it all together real quick, just to get a win. We've got this quantity called flux. We argued that it accumulates. I should clarify. When I say flux, in this context, when I say flux, I mean boundary flux. further reminder, when I say boundary, I mean oriented according to the certain convention that I'll loosely call outward. So when I say flux, in your mind, you should hear outward-oriented boundary flux. I'm just going to say flux. Very common choice, by the way, in this context. People just abbreviate that. Just say flux. So it's an accumulating quantity, and when you have an accumulating quantity and you want to compute a little piece of the whole, right? Stuff is stuff per unit volume, namely density, times volume. Just like any other stuff. When you want to compute mass, you integrate mass per unit volume, d volume. When you want to compute flux, you integrate flux per unit volume, d volume. Okay. And altogether, notice we have ourselves a brand new theorem. It's pretty awesome. Let's see here, color choice. Flux is a triple integral of divergence over the interior. And this is Gauss's divergence theorem. What do you think? Got an application coming up, right? An example, I mean. Everybody see the big idea? Again, my favorite sort of, take on this. Notice how the argument, the structure of the argument we've made, it's just like the argument we made for Green's theorem. We found an accumulating quantity. We treat it as a stuff. We compute a corresponding density, and we do an integral of that density. Same basic idea, different geometric details, different theorem, totally analogous. Okay. All right. Okay, before we do an example of this, let me come back up here, and this is a nice opportunity, I think, for me to follow up on a promise that I made back in Chapter 3. Back in Chapter 3, I made a completely unjustified claim. I just asserted that divergence can be interpreted a certain way. And I just said, well, look, it's kind of in some sense measuring how much the fluid is kind of emanating outward away from a given point, right? And I didn't give you any reason to believe that was true. We didn't have the tools at the time. Well, we totally do now, because divergence, being as it is, flux density being as it is, all these different things, being as it is this, you can literally see that it is computing, let's see here, flux, that is outward-oriented flux, namely, keep in mind, flux means flow of fluid in the direction of the orientation. So this flux means how much is, in the net, how much is the fluid flowing outward per unit, I wanted to be in highlighter mode, per unit volume. So per unit volume. So this is how you see that claim that I made back in Chapter 3. Flux computes a net outward flow. Divergence says, yeah, sure, that's what you're going to get when you at some little point. Obviously, if you look at a small little piece of volume, you're not going to get much net outward flow because look how small it is. Obviously, bigger volumes, you're going to have more net flux, right? But so per unit volume, how much net outward flow do you have? Well, that's exactly what divergence computes. So that's why we make that interpretation. So I hope that's satisfying. It's a nice point of view, I think. By the way, quick reminder, we took an analogous point of view back in Chapter 6. You may recall I like thinking about all of these accumulation theorems by comparison to the fundamental theorem of calculus, the point of which is that change is an accumulating quantity. Right? We compute change by looking at the endpoints, aka the boundary of our interval. That's how you compute change. The formula for change. Yeah, sure, it's at the boundary, A and B. Is that where the change actually happens? Psh, nonsense. Of course not. The change happens in the interior. Specifically, look at that. You can see the change happening, obviously, in the interior. So I know I've said this before. I like to remind you again in this context. Pretty easy to see. I'm not asking much here when I say, can't you see that this thing computed on the quantity actually happens in the interior? Yeah, it literally happens in the interior. Right? And furthermore, the derivative, right, is telling you where and how much. Right? You look at a little triangle here representing the derivative, rise over the run, slope of the line, sure, but you can also think of that as change, our accumulating quantity, our stuff, change stuff per unit size. So you can think of derivatives as being a density. And we explicitly used that interpretation here. If I can get this to cooperate. There we go. The derivative helps us identify where change is happening the most. If you want to compare these 2 points, where is there more change happening? And let's suppose that we, suppose we couldn't just look at the picture and tell is perfectly obvious, right? Where is there more of this stuff called change? Is it at x equals 1 or x equals 2? Well, you look at the change density. If you want to know where there's more stuff, look at where the density is. Look at what the density is of that stuff. The density, f prime, you can plug in these 2 points, and density is higher there, where x is 2. There's more stuff at x equals 2. Therefore, there is more change happening at x equals 2. And again, well, of course, clearly more change happening at x equals 2. So our geometric intuition on this graph corroborates the interpretation that we're making here, that the derivative is interpreted as change density. Right? So I'm going to say we're going to do morally equivalent thing here. Let's ask now, different geometric context, different accumulating quantity, now flux instead of change. Is there more of that at this point or at this point? We've got this stuff called flux. Yes, it's computed on the boundary. Of course it is, right? But we're viewing it as a stuff distributed throughout the interior. Is there more here or is there more there? How do you tell where there's more of that stuff? Well, you tell where the stuff is by looking at the corresponding density. Divergence is flux density. That's what's going to point to where this stuff is. And you can evaluate that stuff density at our 2 points. And again, just look and see. Where's the density higher? Well, that right there, that 75 is higher than 48. So the density is higher at B. The flux density is higher at B. There's more flux happening at B because the divergence is higher at B. Everybody see how this is analogous? Now again, it's geometrically different, of course, right? Here, this is a lot more geometrically relatable. Harder to see the picture when you're talking about divergence, of course, right? But in the same way that the derivative is telling you how much change is happening in the vicinity of a given point, I claim divergence is telling you how much flux is happening at a given point. Yep?
How exactly do we interpret how much flux is happening?
Well, I mean, so, you got to talk per unit volume. Like, if I say there's more change happening at 2, the quibble, perfectly legitimate complaint is, no, at the point 2, there is just a single value. It's not great. But what I mean is, but if you kind of look in the general vicinity of 2, you look at little intervals around there, there's more change happening in the vicinity of 2. And likewise, same thing here. When I say, where is the flux happening, I claim there's more flux happening at B. I mean in the vicinity of B.
Like a very small volume around.
Yeah, if you look at little small volumes around B, there's going to be more flux than at A. That's right. Okay, see y'all later. Have a good weekend. See you on Monday. Don't forget about attendance.